All right, this part of the lesson, we're going to talk about, again, inventory models. We're talking about the case of, again, a continuous review inventory situation and a situation where we have the instantaneous resupply. And what happens here, the change here, is that we're going to consider the situation where we have quantity discounts. So in other words, and as it says here, the price of each item that you're purchasing does not remain constant. And you get a price break. So if you order a certain amount, there's one cost. If you order an additional, larger amount, the cost of those items are lower, and so forth. So there may be several price break points. But everything else with our EOQ remains the same. And we're going to consider the economic order quantity model with this. So again, it says here it relaxes the constant price assumption. And again, it's what we're focused on here. The changes is in our purchase price because there's discounts for larger quantities. Everything else with our economic order quantity model we're saying remains the same. The carrying cost is constant, the ordering cost is constant, and everything else remains the same. And what this does is it creates what's called a stepwise cost curve. And so we're going to look at that and try to determine the lowest total cost. And in this case, we're going to include the purchase price, where there's the purchase cost P times our annual demand. We need to include that in this process, and we'll see that in the example. The next slide is an example from pages 562 and 563, and it talks about that stepwise curve. And so we're given a situation where if we order, and these are just hypothetical widgets, if you will, if we order between 0 and 99, the price per item is $10. If we order 100 up to 200, the price is $8. And if we order more than 200 of these items, the price is $6. And so what happens, because the holding cost and the ordering cost remain the same, the ordering cost curve is here, the carrying cost curve or line is here, and because the purchase prices change, it creates three different cost curves, total cost curves. So these dotted lines represent the total cost, which includes the purchase price. This would be the most expensive, the purchase price at $10. The second curve here would be the next most expensive at $8 per item. And then this third curve is the least expensive at $6 per item. And because on our x-axis we're looking at the quantities, again on our this x-axis is our quantities ordered, and the y-axis is our inventory cost. What happens is that for any number of items that we purchase less than $100, well, we have to pay $10 per item. And so that gives the solid red line that's our total cost curve. And then for the items that we order between 100 and 200, well, we would then be on this portion of the total cost curve, that cost that corresponds to $8 for items ordered between, number of items between 100 and 200. And then, of course, anything above that we order above 200 items will be on the cheapest cost curve, lowest price cost curve at $6 per item. So this red curve is what mathematicians call a stepwise cost curve, because at certain points the price break kicks in and it creates this step here at 100 items and then again at 200 items. So this red curve is the feasible cost curve. Now what happens then when we compute the economic order quantity? As you remember, the economic order quantity model only considers the carrying cost and the ordering cost, and we know when those values are the same, it creates our lowest, our minimum cost in terms of those, in terms of the quantity that's ordered. And in this case, you can see that optimal value in this example occurs between 100 items and 200 items. And so once we compute our Q star, it says Q optimal, but this is Q star. We notice that it falls here, and so it would tell us that once we calculate the total annual inventory cost, it would be here. But the question is, again, is this the lowest total annual inventory cost? And so what we need to do at that point is determine for this point, we need to determine the total annual inventory cost for this optimal order quantity. And then for each lower price breakpoint, in other words, for this point here, we also need to compute the total annual inventory cost. And I'm going to put this total inventory cost 1 and 2 to make sure that we indicate that those are different. And as you can see by the graph, change colors, you can see, even though this line is not going to be straight, that this cost for the total cost for point 1 is more than the total annual inventory cost for 2. And in this case, this would be actually be the ordering 200 would actually generate the lowest total annual inventory cost. Now, there's of course another situation that could happen. Hypothetically, if let's just ignore this for a minute and say that there was this was not the break point, but that the break point occurred, the next order break point occurred somewhere, let's say out here. That this is where, instead of at 200, let's just say 300 was the next break point that went to $6. Well, then we would be on this curve, but in this situation, this total annual inventory cost might be higher than this one. So our curve would look like this. It would go out this way, and then the break point would be here, even though I can't have a thick line. And so again, it could be that even though the total price was cheaper, the total annual inventory cost was lower. So there's an algorithm that we're going to follow, and there's three steps to the algorithm. And the algorithm that we're going to follow is, the first thing is we are going to compute we're going to compute the economic order quantity, and that's going to be Q star. We're going to find Q star. Then we're going to determine where Q star falls on the within the ordering price range. If it's at the lowest price point, we stop. If it's not at the lowest price point, then we compute the total annual inventory cost for Q star that's corresponding to Q star, and every lower price break point. Right? And so let's look at an example and see how that works. And this next example follows. It's on page 563 and 564 of your textbook, and let me read it. And it's the Avtec problem. And Avtec is a distributor of audio and video equipment, and Avtec wants to reduce large stock of televisions. It's ordered a local, has offered a local chain of stores a quantity discount pricing schedule as shown on the diagram. And so the quantity discount, we're ordering televisions, and if we order between 1 and 59, the cost is $1,400. 1 and 49 cost is $1,400. Anything between 50 and 89 is $1,100, and any number of televisions ordered above 90 is $900 per television. So we get as much as a $500 price discount for the number of televisions that we ordered. And we're also told in the problem that the ordering cost is $2,500 per order. The carrying cost is $190, and then the annual demand is $200 per television. Excuse me, 200. The annual demand is 200 televisions per year. Boy, I apologize for my tongue being tied. So given this information, the first thing that we're going to do is find Q star. And we want to know where Q star falls in this within these order quantities. So and we're using our EOQ model. And so we're going to compute the square root of 2 times demand times our ordering cost, and that's all divided by the carrying cost. And so once we substitute in, this of course is the square root of 2 times 200 times 2,500, and that's all divided by 190. And when we do that arithmetic, we're going to learn that that's 72.5 televisions. And that's Q star. So now for 72.5 televisions, where does 72.5 televisions fall within this ordering range? And of course, it falls here between 50 and 89. So then the next step that we have to do is we need to calculate the total annual inventory cost for Q star and compare that to the total annual inventory cost for the case where we order 90 televisions. We're at 90 is our order quantity. Notice it's not the optimal order quantity, but it's or the EOQ optimal, but it is the order quantity that we need to compare. So that's what we're going to do next. So, for example, so for the total, I'm just gonna, the total annual inventory cost is going to be, now we need to include P times our annual demand. And because the order quantity we're going to look at first is 72.5, that order quantity is, our annual demand is 200 times the purchase price, which is 1,100 per television. And now we're going to use our annual carrying cost, which is Q over 2. Again, this is our EOQ model, not our PQM model. 75 over 2, 72.5 over 2 times our carrying cost plus the number of orders that we make, which is going to be 200 orders, 200 televisions, and we're going to order 72.5 each time. And our carrying cost is, of course, $2,500. All right, and when we do this arithmetic, we're going to see that this total annual inventory cost is dollar amount is $233,784. All right, so this is the total annual inventory cost for 72.5 televisions, which is our Q star. In other words, we've substituted in 72.5 for our Q star in our total inventory cost. All right, step 2 is we're going to calculate at the next lower price break, which is here at 90 televisions, we're going to calculate the total annual inventory cost at 90 televisions. So we still are going to need to order 200 televisions, but the cost now, instead of being $1,100, is only $900. Again, notice we're just bringing this down. It's $900, and then plus, and now we're going to use 90 televisions because that's going to be our order quantity. So we'll have on hand 90 televisions times our carrying cost remains the same. And then we're going to have, and the number of orders that we're going to make is we still have to order 200 on the year. And now we're going to order, each time we order 90 televisions. So that 200 divided by 90 is the number of orders. And then finally, we'll have our same carrying cost of $2,500. And we do this arithmetic, we're going to learn that this amount is $194,105. $194,105. So now we need to ask ourselves, well, given these two total annual inventory costs, which one is preferred? And hopefully you would see that indeed this total annual inventory cost for ordering 90 televisions at a time produces a total annual inventory cost that's almost $40,000 less than if we order at $1,100. So we would choose to order Q. Our order quantity would indeed be 90 TVs. And so that's the process for the quantity discount. Now the next slide, this is my crummy handwriting, computer handwriting. The next slide has all of this information here given, and of course our order quantity is 90 televisions at $900 each. And then the last slide summarizes that algorithm. For this situation, we're going to compute the economic order quantity using our EOQ formula. And once we know this, if that's at the lowest discount level, then we stop. We're done. If not, go to step 2, where we compute the total annual inventory cost for that EOQ, and then for every lower discount price, compute the total annual inventory cost and pick the one that produces the total lowest cost. And again, in the previous example, had there been another break at 100 televisions instead of being $900, if the cost had been $800 for more than 100 televisions, you would have done that same process and compared all 3 total annual inventory costs. So that's the process. Again, as always, study your examples and let me know if you have any questions.